So today we're going to do more practice problems with friction. And let's see what we have here. So let's just draw a little cartoon and see what's going on. We've got a 450 gram box, and we pull it across a table or floor with a force of 1.0 newtons. And it says there's friction. Since we're moving the box, this will be kinetic friction. Let's draw our free body diagram. We always have to draw a free body diagram here. mg goes down, normal goes up. We're pulling at 1.0 newtons, and friction resists. The box isn't going to jump off the table. We're not pulling up on the box, so we know that the box isn't going to jump off the table. So the sum of the forces in the y direction is going to be 0. So normal goes up and mg goes down. So we know that normal is going to be equal to mg. Okay, so let's see what we can know. We're pulling at a constant velocity. That's important. Because it's a constant velocity, there's no acceleration. Because it's constant velocity. So you might think, well, the sum of the forces is ma. It can't be. Even if you tried to put the a in there, well, a equals 0. So the sum of the forces is still 0 because it's constant velocity in the x direction. So the force of the pull up here is towards the positive x direction, and the friction resists. So that means the force of friction is equal to the force of the pull. All right, well, friction, if we remember, is mu k times the normal equals force of pull, or mu k, now we said normal is mg, times the force of the pull. And sorry, I'm running out of room here. And let's see what we know. We don't know mu k. We want to calculate that. The mass of the box is 0.45 kilograms. Watch out for that. Times 9.8. Has to be equal to the force of the pull, 1.10 newtons. So at this point, all we have to do is a little math. So let's see, 0.45 times 9.8 is 4.41. So I've got 4.41 mu k is equal to 1.10 newtons. We're going to divide both sides by the 0.4 or 4.41. I think we can almost see this. See, it's 1 over 4. It's got to be close to 0.25. And in this case, it is 0.25. Just to remind you from the previous video, there are no units on friction, on the coefficient of kinetic or static friction. It's just a factor. It tells us how rough the table is. So this table is about 0.25. That's not unreasonable. Usually when we do the lab using the benches that we have here, we get around 0.2, 0.3. So that's absolutely a believable number. If we really wanted to double check, we could come back here and see, okay, wood on wood, kinetic is 0.3. We got 0.25. Absolutely believable. So let's go a little further down. Okay, now we've got a sled that we're also going to pull at a constant velocity. And we want to know what force is required if the mu k on is 0.11 on ice. All right, so let's take a look at that one. We'll draw a free body diagram. mg always goes down, normal goes up. The force of the pull is towards the positive x direction. You say, well, what if you're pulling the sled the other way? We'll make that the positive x direction. It makes sense to make that positive. They're telling us the friction kinetic is opposite. So I think we can see that the normal is going to be equal to mg here. I don't think we need to go through the full sum of forces in the y is 0. We just did that. Now we have to see, well, what's the sum of the forces in the x direction? It's a constant velocity. So that means the sum of the forces is 0. That means the force of the pull is in the positive direction. It's going towards the positive while the kinetic friction is resisting. So let's see what we got here. What force is required? So we don't know the force of the pull, but we do know the force of friction. That'll be mu k times the normal. So let me just move things around here. Force of pull will be equal to mu k times the normal. And we already said normal is equal to mg. If there was an additional force, if somebody was pulling up on the sled, like if you were pulling at an angle, then things would be different. But in this case, there's no additional forces, so normal just equals mg. So force pull is mu k mg. At this point, it's pretty straightforward. We just substitute. So mu k is 0.11. That's reasonable. This is ice. It's going to be pretty slippery. The sled is 2.5 kilograms, and gravity is 9.8 meters per second squared. I should remind you of the units here. So now I can put it in my calculator. You can hear me crunching away on the machine right there. And I get 2.7 kilogram meter per second squared, which means the force of the pull is 2.7 newtons. That's not a big pull, but we're on ice. If you've ever pulled a sled, somebody's on the sled and you pulled it on ice, you know that it's very, very easy to pull it on the ice.